So it's just odd how people figure stuff out. So in case, because a student in my first block chem class comes in and says, "Oh, I hear you're going to do this." So here's a short version in case you hear it. It's a good thing. But I wrote a children's story, and it's called Loopy, the Spirit of the Cow Dog, and it's been published. It'll be out before Christmas. And if you're familiar with Watermark Books, they're actually going to have me do like a reading of the story in their store the Saturday after Thanksgiving at 10 a.m. It's like buy a local business. And so anyway, if somebody sees it, because they've got it on their Facebook page and everything, and so I don't go, why didn't you tell us? Okay, I told you. So there you go. And yes, if you want to buy the book, I can get you a
Can you read
copy.
it to us?
I will read you the book.
Will you?
I
Yay!
promise you.
When?
Well, I actually, they're going to be sending me like the trial copy. Hopefully I get that this week. As soon as it gets in, I will read it to you guys. So you guys can hear the story. Anyway, so there's that. So each year has kind of done a different thing as to raise money for the solar project. So I will talk more about that later. Like last year, I dyed my hair like red and green, and that was it.
Get a piercing.
No.
Belly button piercing.
Oh my god, I'm getting one in December. You want to come too?
The world
We
will
can
burn
all get belly
first.
button piercings.
Okay?
We can go
I already did
together.
that.
You should get a
So, yeah, I already did the tattoo thing, so that's...
What's something like
ear piercing cat.
class pet? You should get like a lizard.
No. Okay, I got the children's story. That's what's going on
I know,
this
but a
year.
class pet
So,
would be so fun.
do what?
A class pet.
No.
Physics lizard.
No.
Oh yeah, a lizard or gecko
He already has fish.
or a
Well, I've
guinea
got the
pig.
fish down there at the end of the hallway. That's all.
You should skydive.
Oh my! Mr. Burkett, do you want to see this really funny video of a possum that was on my deck? It's
I
actually
don't know
really.
where we do skydiving other than the connection is playing dead.
Skydove a little bit.
It did a little bit.
Skydiving, that's a good one.
Okay, I have a problem with skydiving. One of the first things they tell you is something called terminal velocity. Okay?
Oh my gosh.
So when that involves the word terminal and I take a lot of physics, I'm not sure that I'm all in on that concept.
Terminal
So-
Who
velocity
knows all the
zero.
math? That's weird.
Okay, so let me give you some hints on some of the answers that you should get on this big assignment. It's actually going to be due tomorrow, okay? And yes, I've got the review and everything else, so I've got that going. So when you look at like question number 1, and with that one, the whole key to that one is that you're going to find the mass of the marble. So if you look at these equations that you need to know for the test tomorrow in terms of the planetary motion, you got Kepler's laws, TA squared over TB squared equals RA cubed over RB cubed, okay? And all that, like I showed you yesterday, that all just comes from Newton's, that big Swiss Army knife equation that says 4 pi squared r cubed equals big G mass T squared. So this comes from a comparison of 2 moons, 2 planets, whatever, that are orbiting the same center. So this comes out of Newton's laws if you go far enough back. Now, this one is the only time I will ever hear you will ever hear me say this. Doesn't matter what the units are, as long as they're the same. Okay? So you can work in. People don't know my door's open.
Are you busy?
Yes.
Kinda. Why?
I was wondering if I could interview Gracie real quick.
Oh my gosh.
You're
Okay,
so
she
famous,
says-
Gracie.
Are drinks involved? Okay. Are you busy? I'm just in front of my class, nothing important happening. Okay. So, anyway, back to our story. So, this is a cool thing. It works well, but there's a couple of conditions. They just have to be the same. So this is the only time you could work in days, you could work in years, you could work in weeks. Doesn't make any difference, okay? Because it's just gonna be a ratio. The same thing is gonna be happening with radius. It could be in meters, it could be in astronomical units, it could be in anything, because it's just a ratio. So that is the only time you will ever hear me say that. Now, however, once you get into the big three, little g equals big G, mass, r squared, v equals the square root of big G m over r, and then the Swiss Army knife. As soon as you see anything that involves big G, okay, remember, hidden within that are newtons, which are kilograms meters per second squared. So as soon as you do any calculation that involves big G, it is the quintessential rule of the MKS system. You can only work in meters, kilograms, seconds.
I agree.
What are you looking at?
What's going on?
Stan, what are you doing?
Yeah, what?
Stop.
So, just keep that in mind, okay? Because that is the most common mistake. And then what happens is that you get orbital periods that are like, for example, I'm going to tell you straight up on the test, you're going to have to calculate how long it takes for the lunar command module to orbit around the moon. If you don't do it right, you're either going to get a time less than 1 second, okay? Which seems weird, like you're going to go orbit all the way around the moon in less time than it takes to snap your fingers. Or you're going to get a time of like either years or hundreds of years. The worst I ever got was longer than the universe itself has existed. So, more so than any other test, you have the capacity to get answers that make no sense. If you don't do the math right, you don't do the conversions right. That's the most important thing. Okay, so on number one, basically all we're saying is you're going to go, oh, F equals big G, M1, M2 over D squared. So this is like the mother of all equations, because everything else spins out of this. Okay, that's it. This is the one. So like, let's say for example, you wanted to calculate how much you weigh right now. Here's your challenge. What do you weigh on Earth? Oh, okay. So you could plug in your mass, say 60 kilograms, the mass of the Earth, 5.979 times 10 to the 24th kilograms. However far you are from the center of the Earth, you can just use, typically it's about 6.3713 times 10 to the 6th. And you can calculate that first, okay? It's a long way to do it, but you can do it that way. Because fundamentally, that's what's happening. Now, typically, we shortcut that and we go, oh, FG equals MG. So on the test, remember, if I'm asking you to find a weight, weight is a measure of force, and that's going to be in newtons. If I want you to find mass, that's going to be in kilograms. So when there's a problem on the test, notice I did not say if, I said when there is a problem on the test, and I ask you to figure out how much something weighs on Earth, maybe the moon, Mars, something like that. So when you say, what does something weigh, I'm asking for a force in newtons. If I want mass, I'll ask for that, and then you give that answer in kilograms. So keep those two things straight. So anyway, so on number one, you should get something times 10 to the minus second, okay, which isn't very much because you're finding the mass of the marble. When you get to number two, the whole key to number two is the word identical. So you're still going to go on number two, you're going to still start with this. F equals big G, M1, M2 over D squared. Because they're identical, that's X, okay? And when you multiply X by X, what do you get?
X squared.
X squared. Do not tell me it's 2X. Now, let's say, hypothetically, let's say I said, here's the force, but one of the masses is twice that of the other. If I had said that, what would you do? Then you'd have x and 2x, okay, which would get you 2x squared, okay? So, promise you, there's gonna be a question like that on the test. I promise you, there is gonna be something like number 2 on the test. Mark my words. When you get to number 3, again, this is, notice on there, number 3, I've got the word, how much is something going to weigh, okay? Weight is a measure of force. So, conceptually, what I'm looking for on number 3, how tall is the tower you're gonna have to build so that when you drop something, it accelerates at 3 meters per second squared, okay? So notice on this one, I'm asking for the center to center distance. So this is going to be from this point down to the center of the earth, okay? This is what you're looking at. So the easiest, there's a couple of ways you can do this. One is that you could go old school and go, well, I want this thing to weigh 3 newtons. Fundamentally, that's what you want, okay? You want this thing to weigh 3 newtons. You've got big G. You know, one of the masses is the earth. The other one is 1 kilogram. And you're trying to solve for distance. Okay, so conceptually, that's the most important step. Oh, something has a weight because of a gravitational attraction. So one option is that you go 3 newtons, big G, mass of the earth, 1 kilogram, distance squared. It's one option, okay? Now, the other option that you could do, and I don't care how you do this, the other option is that you realize, wow, I want little g to be 3 meters per second squared. I know big G, I know the mass of the earth, I solve for R, okay? So this process makes the math probably a little bit easier, okay? This is this version over here with the 3 newtons, that's more conceptually clearer in terms of what's actually causing the forces. This is mathematically more easier, okay? More easier, not more easier, easier. But no matter what, your answer to number 3 should be something times 10 to the 7th meters, okay? Pretty big distance. When you get to number 5 and you're calculating distance between Uranus and Neptune, okay, that's like the average distance between them, which obviously changes depending upon where they are in their orbit. That answer to number 5 should be something times 10 to the 16th. Pretty big number. Now, let's talk about number 6, because 6 is important conceptually. If you all hearken back to your Chem 1 days, which for some of you might have been a long time ago.
That was last year.
Yeah. So does anybody remember what Ernest Rutherford did? Oh dear Lord.
Did he make one of the models?
Let me give you a hint. He
Plum
did
pudding?
gold foil.
Oh, he did
Foil?
the experiment. You shoot the electrons and they pop back sometimes.
Close. Okay? Ernest Rutherford had the gold foil and he shot alpha particles at the gold foil. Okay? Didn't even know what they were, I just called them alpha particles. Turned out they were a helium nucleus that had the electrons stripped off of it. So it's He4 2 2+. Okay? So figured out the gold foil, even though it looks solid, is 99% empty space. All of the mass is concentrated in one very, 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 very small area. Now, if you look at Ernest Rutherford, Niels Bohr, Erwin Schrödinger, Max Planck, the chemistry department talks about this, but all of these guys were physicists, okay? They were all physicists. All the big hitters, you look at the chemistry class and they talk about that, they're all physicists. Basically because they didn't have anything else to do, so they figured, okay, hey, let's figure out the structure of the atom, okay. So when they figured this out, you have to understand these guys were happy because they're going, oh, this is like a little solar system. The nucleus is like the sun, and the electrons would be like the planets. Simple. That's why when you look at like the Bohr model, that's what it looks like, because these guys were physicists. And they said, oh, just like Earth orbits a certain distance away from the sun, electrons are going to orbit a certain distance away from the nucleus. Okay? And they were happy with that thought. The problem is they couldn't explain why the electrons don't lose energy and collapse into the nucleus. That presented a small problem. But that's a whole other discussion. So basically they said, okay, what are the forces involved? Because they were physicists. They said, okay. So on number 6, the first thing you want to do is figure out the gravitational attraction between them. So on that one, that's a very, 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 very small number. So your answer to number 6A should be something times 10 to the negative 47th. Okay? It's a really, 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 really small number. So this created a huge problem. Because now they're going, well, gravity can't hold it in place. Because in other words, so this electron is moving around. So speaking of which, so imagine this. Here's an electron going around the nucleus, right? Is it accelerating? Yes. Okay. Is the velocity constant?
Yes.
No, it's accelerating.
It's changing direction.
If it's accelerating, can the velocity be constant?
No.
No. By definition, what is acceleration?
Change in
A
velocity.
change in velocity. Okay? That's what the definition of acceleration is. But what's making it accelerate? A change in the magnitude or the change in the direction? Change in the direction, which requires a force which acts
Inwards
at right angles to the
velocity.
Okay. So, what they thought might be happening is that imagine I'm the nucleus, and imagine that's an electron. Okay, first off, the electron would be traveling close to the speed of light, which means we can't even see it, okay, and it's a tiny bit of matter. So they said, well, maybe, just like the Earth holds in orbit by the gravitational pull of the sun, maybe the nucleus creates a gravitational pull to hold the electron in place. Okay? Problem is that it's way too small for gravity to provide it. They said, okay, well, so much for that idea. They said, well, maybe the electrostatic force. So the electrostatic force, remember, that's the one between oppositely charged particles. Okay? So I tell you that that's 8.2 times negative 8. And I said, okay, well, let's compare these. So when you compare these, what you'll see is that your answer to 6B should be around something times 10 to the 40th. Okay? So the electrostatic force is about 10 to the 40th. Okay? Not 4 times greater, but like 10 to the 40th times greater. That created another problem. Okay? So imagine that I'm swinging this thing around. Okay? Let's say this is the Earth and I'm the sun. And then all of a sudden, the force of attraction between the Earth and the sun increases by 10 to the 40th. Whoop! Right there it goes. Okay, we are screwed at that point because the Earth cannot orbit the sun if that gravitational force increases by like 10 to the 40th. Okay? So that created a problem. It's like, well, why do the electrons not collapse into the nucleus? If there's that much attractive force, the electrons should immediately basically spin in, and we should not be here having this discussion. I've had this table since the fall of 1994. I've been teaching behind this table since the fall of 1994. I walk into this room, I worry about a lot of things. What I don't worry about is this table turning into a square. Okay? Don't worry about it. So whatever that model was had to explain the stability of the atom. And what they figured out, this is where Erwin Schrödinger comes along, and basically they travel in waves. And because they travel in waves, they can only exist in certain energy levels. So that's what basically solved the problem. On C, that answer, what would be the mass of the proton to have that much gravitational force? That answer should be really, really big, like 10 to the 12th. Okay? So in other words, if gravity is what had to hold it in place, not your entire body, okay? But a single proton would have to have a mass of 10 to the 12 kilograms, okay? Y'all know what you get the idea how heavy a kilogram is. Now you can have like 10 to the 12th of those, and that's just one proton.
How many kilograms are in an elephant? Like, if it's a ton? Because isn't it like 1,000?
Probably, in round numbers, probably about 1,000.
1,000 kilograms?
Yeah,
Wow, that's a lot.
yeah, that'd be a lot. And that's just one. Okay. Both of your answers to 8 and 9 should be something times 10 to the third, oddly enough. Now, make sure that you're cool on number 8. So have this visual. So here's the moon. The moon itself has a radius of 1738 kilometers. So right away, what are you going to have to do with those kilometers? Change it into, multiply by 1,000, don't divide by 1,000. Don't tell me the radius of the moon is 1.738 meters. I'm taller than that, okay? Now, the whole kicker on this one is that it's 72 kilometers above the surface of the moon. Trust me, here's what you're going to do wrong. You're going to take those 72 kilometers, and you're going to change that into meters, and you're going to go, score. I didn't lie to Burkamp. I changed it into meters. Yay for me. And you're going to use a radius of 72,000 meters. Okay? Wrong, 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 wrong. What do you have to do? You have to add in the moon's radius because it has to be a center-to-center distance. Okay? Even when you're orbiting the moon, orbital period should be something times 10 to the third seconds. Orbital velocity should be something times 10 to the third meters per second. And so help me. You remember that the speed of light is 10 to the 8th meters per second. If you have the urge to write down an orbital velocity anywhere close to the speed of light, 10 to the 5th, 10 to the 6th, better yet, I've actually gotten velocities faster than the speed of light. Stop. Don't. Okay? Look at that exponent. Okay? Remember 3 for the win. Okay? 3 for the win. Okay. Number 10, both of your distances, those Lagrange points, should be something times 10 to the 8th. Do not forget to answer that question about what happens as it crosses that first Lagrange point. If you want a visual, here's the gravitational well of the Earth, here's the gravitational well of the Moon. Basically, what's going to happen there. If you like that idea of a gravitational well and you want to explain it that way, that's cool. If you want to explain it in terms of forces, okay? But here's what I don't want you to say. This is the answer I do not want. Do not tell me, oh, as soon as it crosses the Lagrange point, it gets pulled by the moon. No. Right now, you all are being pulled on by the moon, okay? You are. I don't worry about it. It isn't like, wow, it's a full moon and I'm going to start being, pulled off the surface of the Earth, okay? There is a gravitational pull. It's just not very much. So just don't say, oh, then it gets pulled on by the moon. You can talk about net forces, okay? That's kind of an easy way to explain it, but just don't tell me, oh, then it gets pulled on by the moon. That's bad. Your answer to number 12 should be something times 10 to the 26th. When you hand in that test tomorrow, if you have not found the mass of a planet using that Swiss Army knife equation, you have done something wrong. Okay? I promise you, there is going to be one like number 12 on the test. I promise you. Okay? I'm going to give you information about the moon of Saturn, Neptune, whatever. Okay? And you have to find the mass of that planet. And I promise you, in what units is the orbital period not going to be in?
Hours.
No.
What do you mean?
It's not going to be in seconds.
Oh, you're not going to give it to us.
I'm not going to give it to you in seconds. Okay? What are you going to have to do?
Convert it.
Convert it into seconds. Okay. Promise you. When you get to number 13, here's the deal. here's the satellite orbiting around, okay? Geosynchronous orbit, what that means is that if you're into like paranoid and conspiracy theories, like, oh, the government is watching me. Yes, there are satellites parked directly over us right now, watching us. But that's cool, because if you don't have those, your GPS system on your phone doesn't work, okay? And everybody's, oh, they're gonna put microchips in us. Shut up. They know more information off your phone than they're ever gonna know from a microchip, and quite frankly, the government just doesn't care. Get over yourself. Don't flatter yourself. The government's tracking me. No, the government doesn't care. So, the whole point of this being is that, there are satellites directly above us, okay, they work. This is how GPS works, it's a triangulation of data. So when you find that radius, that's a distance from the center of the earth out, okay, which doesn't do us much good in terms of calculations because of the fact that we're not in the surface of the earth. Or we're not in the center of the earth, we're at the surface of the earth. So from your calculation standpoint, you need to know, oh, that signal is going to bounce off me when I'm at the surface of the earth, not when I'm in the center of the earth. So that's why you do that. So you should get something on 13a, that should be something times 10 to the 7th, okay? As that distance. So the reason that, and I do this on number 14 as well, it's tough for you to realize, hey, let's make a little bit of a comparison. So what you should see on 13b, I'm comparing this from the distance from Wichita to Kansas City. And what you should see on number 13, that distance is off, is like about a factor of 100 times greater. So in other words, if you're in this geosynchronous satellite, you're about 100 times farther from the surface of the earth than you are from here to Kansas City, okay? That was the whole point of this. But then when you get to C, you're trying to figure out, hey, how long does that take for that GPS signal to travel from your phone out to that GPS satellite? So what you should see is that that answer for 13C should be around 0.1 seconds, okay? 0.1 seconds is about how long it takes for you to snap your fingers. So this is why there isn't like a time delay. So you've got your phone, you're trying to figure out, hey, how do I get to Watermark Books to watch my physics teacher read a children's story? You plug in Watermark Books. It's going to keep, as you're driving, it's keeping track of where you are. It's continuously sending these signals back and forth off of these satellites. And for you to go from that signal from your phone to those GPS satellites is about that long. Okay? So that's one way. So that's why it can keep such precise locations, because there isn't this big time delay. Now, one of the things I might ask you to do, okay, is say, okay, calculate the centripetal acceleration of that satellite, okay? So if I ask you to calculate the centripetal acceleration of the satellite, which I promise you I'm going to, okay, again, when you hand in your test tomorrow, if you haven't calculated the centripetal acceleration of the satellite, you have done something wrong. Now, let's start at the beginning. As that satellite goes further and further from the Earth, what's going to happen to the value of its centripetal acceleration? It's going to become smaller and smaller and smaller, right? At near Earth orbit, if you were right at the surface of the Earth, if you could put a satellite in orbit right at the surface of the Earth, we can't because we have an atmosphere. But if there wasn't an atmosphere, what would be the centripetal acceleration of that satellite right at the surface of the Earth? Yeah, 9.8 meters per second squared. Okay, that would be it. That's our kill. There you go. So obviously, as you go further and further and further from the center of the Earth, what's going to happen to that value of G? It's going to become smaller. So if you calculate the centripetal acceleration of a satellite and you get an answer bigger than 9.8, you have done something horribly wrong. Okay? That answer has to be less than 9.8 meters per second squared. So basically, remember your centripetal acceleration is the same as your gravitational acceleration. So when I ask you to do this, and I'm going to on the test, there's a couple of options. You could use v squared over r if you know the orbital velocity of the satellite. You could use 4 pi squared r over t squared. You could find it that way. You could find little g using big G mass of the Earth over r squared. Same answer, just however you want to find it. But, notice all of these are dependent upon a radius. Do not use the radius of the Earth. It is not at the surface of the Earth. This thing is millions of kilometers away from the surface of the Earth, okay? So don't use the radius of the Earth. You're not at the Earth. You're out in space. So keep that in mind. Your answer to 15 should be, oddly enough, be something times 10 to the third. And what I wanted you to see on 14 is that if you go to like the International Space Station, it's actually closer for you to drive from here to Kansas City than it is to get to the International Space Station. Okay, everyone says, oh, he's out in space. Literally, if you could like lay out a line from Wichita to Kansas City and then stand that up, the International Space Station is closer than that. Okay, we just have to get it above our atmosphere. So that's why I kind of have that as some perspective. Literally, the distance to Kansas City is greater than the distance to the International Space Station. Yes?
So we could take a field trip to the International Space Station?
Well,
It's so close.
yeah, we could.
So
but
wait,
no.
what's the travel time then?
It kind of depends upon how big the rocket is.
That
Yeah.
makes sense.
If you've never seen the Starlight satellites, has anybody seen that?
I have.
Okay, if you never have, I'm sure, did we talk about this yesterday?
Was
Yeah,
it like
if you
10
haven't,
in a row?
you should be able to Google it. And it does. The first time I saw it, I thought it was like an alien invasion. So it is. It's just this string of satellites going across. It is cool to see. If you've never seen it, obviously it's going to be cloudy for the next couple weeks. But next week's supposed to be pretty clear. So if someone wants to look that up for next week, then you can go out and see it. It doesn't last very long, but it is cool to see. I got a text from one guy. He was out hunting and he saw it, and he texted me. And he was flipped out. He said, "Burkamp, what is going on?" And he sent me a picture of it. It's like he thought it was like an alien invasion. On 16, you're just going to go old school that equation. Okay, old school that equation. On your answer to 16A would make a phenomenal GPA on a weighted scale. Okay. And your answer to 16B would make a not so good GPA. Okay. Now, when you get to 17, and here's one of the most important questions I want you to get. Okay. First off, when I tell you that you want to explain in terms of mass, inertia, acceleration, and gravitational force, guess what? You should probably have those words in your answer. Okay? I even wasted more ink by making them bold and underlined. Okay? Have the ink not have died in vain. So here's the basic idea. Visualize this. Here's Hank, okay? And here's a rubber stop. I'm going to let go of both of them. Do they both have the same amount of gravitational force acting on them? Jack Randy. Hey, if you're handing out,
Only one.
You know I have to write this test after school. Do you really want me to be angry when I write the test?
You haven't written it yet? What? No.
Don't make me write the test angry. You want me happy when I write this test. Okay. So, I tweaked the test from year to year. So,
Oh, you do?
Don't most teachers do that?
I don't know.
Most teachers just off the internet.
so
Yeah, that's
Those
true.
are the best tests. Yeah.
here's Hank.
Franklin's.
Here's Stan the stopper. Okay? I dropped them. Do they both feel the same gravitational force? Topher Knizzo.
No, of course not.
Which one feels more gravitational force? Hank does. Why? He has more stuff, right? So there's more stuff in Hank interacting with this rock that we're on, right? There's less stuff in Stan the Stopper, which is tough to see. Okay? So Hank has a much bigger gravitational force. But which has more inertia? Hank or Stan? Hank does. So there's more stuff in Hank that resists a change in velocity. Therefore, you have to have more stuff acting on Hank. Excuse me, you have to have more force acting on Hank because Hank has more inertia so that you end up with the same acceleration. I promise you, I'm going to ask you that
That is
question.
not what I wrote.
Can you restate that?
I thought we were talking about the equation, so I was like,
Restate
oh,
it in
mass
really
is the only thing in the
simple
equation that's
terms.
not constant, so that's why, you know?
Don't
So
read
here's
my
the short
answer.
version. Objects with more mass do not use what, you're going to make the sound much better. Here's the short version.
Oh, nuts.
Objects with more mass have more stuff. More stuff has more inertia. Okay? But more stuff weighs more. So you have to have more force acting on more stuff to get the same
You're
acceleration.
talking really fast.
Rewatch the video.
Objects?
A larger
The what?
mass has
I
more.
know, but like, I want to get it done now. You know?
For God's sake.
More mass, more inertia, more stuff.
So more force on more stuff to get the same acceleration.
More force. Okay.
Now,
So it has nothing to do with the equation.
It's such a short answer. I like it.
so let's talk about acceleration. What are the only two things that determine the acceleration of a dropped object?
The mass and the radius
Okay, which mass?
of the
The
center.
mass of
the
what's
center.
being dropped,
No, the
or
center.
the mass of what is of the planet that it's falling towards?
The celestial body.
Ooh. Ooh. Sounds like a pickup line at a NASA convention. Okay, so I'm just saying.
I read that when I looked up the escape velocity.
Okay. So it's whatever you're following towards. Okay. So what this means is this is why Hank and Stan the Stopper end up with the same acceleration. Because the only thing that determines that acceleration is big G, which is a constant, the mass or whatever you're falling towards, and the radius. Maggie canceled out of the equation. Okay, nothing personal. Okay, just cancel that. So, what determines the value of little g is not the mass of the object that's falling. Yes, ma'am.
Hypothetically, if I accidentally left one of the parts of a question, can I put it at the end of the worksheet because there's not enough space to where it's supposed to be?
No, you have to go in.
Oh,
But what if it was?
Yes, just
Okay.
make a little note, put an asterisk, said, hey,
Okay.
to be continued. Looks like a sequel. Okay. Now, is little g a constant throughout the entire Earth?
no.
No.
No, it's not. It changes. Why?
Radius.
The radius of the Earth is not a constant value. Where would little g?
What's just
What kind
happening?
of hair? This thing came off the Reese's.
It was my recess.
I think it was. Reese's hair pieces. Okay. Donald Trump. All right. So,
We're supposed to just get some.
where are you going to weigh more? Listen to me very carefully to that question. Where are you going to weigh more? Here in Kansas or in Denver, Colorado? Why?
Lower elevation.
Less
Yes.
rate.
Okay, so little g in Colorado is a little bit less than what it is here, okay? You climbed to Mount Everest, it's gonna be a little bit less there. Okay. Now, let's talk about this concept of escape velocity. So, visualize this. There's a couple of ways you can look at it. So, the equation for escape velocity is not on your big dog equation sheet. If you need to actually do any escape velocity calculations on the test, I will give you that equation. So the only thing that changes between normal velocity and escape velocity is that there's a 2 in there. Okay? That's the only difference. That 2 comes from the conservation of energy. Kinetic energy is 1/2 mv squared. We'll talk more about that later. So visualize this. I take the rubber stopper and I throw it up in the air. Okay? It goes a certain distance. I throw it faster, it goes higher. So I throw it faster and faster and faster, and it's going to go higher and higher and higher, right? So what's going to happen if you imagine gravity as being like a gravitational well? So the faster that you throw that ball, the farther it's going to go before it starts to roll back down. So escape velocity is basically how fast you would have to throw that thing to get completely out of a gravitational well. Okay? So what they theorized is said, okay, what if we Hello. Hi, Joel. Yes, I can do that. All right, bye. Topher, get out of my room.
Sir, yes,
There, before you go.
First of all, because the gravitational force often of an object depends on the gravitational.
Oh my god.
Wait, no, I got you.
I'm not done. I'm trying to put the pencil no.
Just to make up for the heroin.
I can't do this anymore. Wyatt, shave your beard.
He has a beard?
Look,
Oh.
it's hideous. Sorry, I didn't
Oh
mean
my
hideous.
god.
That was me.
Okay,
I mean, it's not appealing to me.
so what they theorized, they said, okay, if you look at this equation, clearly the bigger the mass is, the bigger the escape velocity is going to be. So they said, okay, what if we set the escape velocity equal to the speed of light? So in other words, even if you were traveling at the speed of light, you still get out of that gravitational well. That was the whole idea of black holes, is that that gravitational well is so deep, even if you shine a beam of light out of it, it can't escape out of that gravitational well. And black holes are a whole other discussion. You have things around them called event horizons, that if you cross the event horizon, then you're basically crossed the point of no return. And weird things happen at the event horizon. There's a concept known as spaghettification. And no, that's what it's called. It's a cool term. But basically what it means is that as you begin to cross that event horizon, that there's such an intense difference in the gravitational field from one side to the other. Like if you went in their feet first, your body would get stretched because of the difference in the gravitational fields. And so that's what the term spaghettification means. Like you would literally turn into like a piece of spaghetti if you could stretch that far, which you really couldn't. Small fragments of your cells and bones tearing apart. But that's the concept. It's called spaghettification. So the only difference is that there's a 2 in there. Now, this mass is what's at the bottom of that gravitational well. So like if we want to go to the moon, we're going to be talking about the gravitational well of the Earth. Because obviously, if I'm going to go to the moon, I got to throw this thing pretty fast to get out of the gravitational well, or otherwise it's just going to fall right back. So that's what that's talking about. And your answer to number 20, to give you some perspective, should be something times 10 to the 35th. So there's that. All right.
Nice.
Anything else on that? Okay.
No, sir.
So that's kind of the big review for the planetary motion stuff. I'm not going to ask you to know like the specific names, like who Tycho Brahe was, the gold nose guy. Nothing really that specific. What I am going to expect you to know as that planets get closer, what happens to their velocity. It increases. Make sure you go and you look back over that whole lab that we did on Kepler's laws. Law of equal areas and equal times. Okay? Make sure that you understand that lab. Make sure that you remember that I'm going to pick one of these equations. I'm either going to pick the one for little g, the one for velocity, or this one, solve for period, and ask you to do the dimensional analysis. So I might say, hey, prove that that equation gets you units of meters per second squared. Prove that this gets you velocity. The one for t gets you seconds. Okay? Now I'm going to tell you, here's the most critical thing that you have to do. At some point, when you've got big G, you've got to come in there and do that substitution where you go big G is newtons meters squared over kilograms squared. That's the first substitution that you have to do. And then at some point for the newtons, you have to come in here and put kilograms meters per second squared. If you want to start right from the get-go with that for newtons, that's cool. So here's the deal. As you prepare for the test, you know I'm going to pick one of these three equations and ask you to do dimensional analysis. You know I'm going to pick one of the three. Okay? It's not a trick. It's like, oh no, he's going to tell us these three, he's going to pick another one. No, it's going to be one of those three. Okay? It's going to be the roll of the dice. Make sure that you can do them. Work these again and again and again. You know this is going to be on the test. Okay? Do flashcards. Oh, right that equation on one side. On the other side of it, do the dimensional analysis to show that it works. Okay? You know that's going to be on the test. Okay? You know without fail. If you can't do it, come in during lunch and say, hey, Burkamp, oh man, I thought I knew how to do this. And I'll make sure you know how to do it. Okay? Now, you listen. On that step, when you do this dimensional analysis, it is not Christmas. This is not the season of miracles. Things don't magically disappear. You show every step of the calculation.
No numbers needed though, right?
No numbers.
Yeah.
Just cancellation of units.
Yeah.
Okay?
Get me for Christmas.
All right. Now, let's talk about the centripetal motion part of it. There's going to be two broad ideas. One idea is going to be something where you're going to have like horizontal. So let's say, for example, I put this rubber stopper on here, and I begin to make it spin. So at this point, is the rubber stopper undergoing centripetal acceleration?
Yeah.
Yes. Why?
Circle.
Moving in a circle. So as this thing goes around, what are the three forces acting on that stopper?
Centripetal.
Centripetal acceleration, or force which is going to act which way? Okay. So here's the rubber stopper. There's Stan. So we got some centripetal force acting this way, and what's creating the centripetal force?
Friction.
Friction. Okay? Friction is. I do have a string, but it's not tied to anything, and there's not like a gravitational well in the center of the green spinning thing. So that force friction is what's creating that centripetal force. Okay? We'll get into that later. Bank that idea right now. What else is there? Gravitational force and your normal force, right? Okay? So here's the kicker. You know that mu equals force friction over force normal. You also have to keep in mind what equations you're gonna have on that equation sheet and which ones you're not. This is the only one that's on your equation sheet, okay? But what you have to realize is that, in this situation, force friction is creating the centripetal force, okay? Now you can make that substitution. Centripetal force is mass times centripetal acceleration. Force normal is the same thing as your gravitational, which is mg. So you can look at that in terms of a ratio of centripetal acceleration to your gravitational acceleration. And that's going to be true whether you've got a situation like this, or if, let's say, for example, whoa, hello. So, years of sitting through boring physics lectures, I really got good at doodling. I was either that or fall asleep. So, and I can't sit there and go, yeah, physics lectures can be horribly boring, I'm just telling you. So, you go, no, Mr. Brookham, no, they can't be. Yes, they can, don't lie. Okay, so here's this car driving around in a circle on a flat track. Is it accelerating?
Yes.
Yes. Does your car accelerate when you turn?
Yeah.
Yes. What's creating the force? Friction. Guess what? If you don't have friction with your tires, what are you going to do? You're going to move in a straight line because there's no force friction. Okay? So whether you have something spinning on a green spinny thing, or if you have something car driving around, that's the story. Okay? They're both situations. Friction is what's creating that centripetal force. Now, I take my 2 Kit Kat bars. Thank you very much, Cooper. I have them go around on the green spinny thing. Which one is undergoing the greater centripetal acceleration? The one on the outside, the one on the inside, or is the centripetal acceleration the same because it's on the same spinning
On
object?
the outside.
Why?
The radius is larger.
So what?
So it'll be larger.
Why? Great, it has a big radius, so what?
Centripetal acceleration.
In what equation?
Yeah, AC.
Perhaps AC equals
E squared over 1.
4 pi squared r over t squared? Do they both have the same period?
Yeah.
Yes, they both take the same amount of time to go around. So as the radius gets bigger, your centripetal acceleration gets bigger. Therefore, you need more force. I promise you there's going to be a question like this on the test. Okay, it's going to involve a record player. Okay? Now, as this goes faster, what's going to happen to the outside Kit Kat?
It'll fall off.
It's going to fly off. Why?
It'll, the net force from, right? No, maybe not. I don't know. Oh, it's the mu, the coefficient of friction.
What about it?
It's, yeah, too big. You know, it can't take it can't take it.
Okay, how about this? Is there a limit to the frictional force that's available?
Yes.
Yes, and if you exceed that, what's going to happen? It's going to fly off. Okay? It's going to, whoop, there you go, right? Now the inside stays on there because, does the inside stay on there because it has more friction? No. It stays on there because it doesn't undergo as much centripetal acceleration. Okay? Promise you, there's going to be a question like that. Now, let's talk vertical motion. Okay? This is going to be the second part of the centripetal motion part.
Me too.
As this rubber stopper goes round and round and round, when is the string going to be most likely to break? Top, bottom, sides? Bottom. Now, again, on your equation sheet, you're not told that the total force that you experience equals force centripetal plus Fg. Okay? That's not on there. It's not there. But you think it through. And you go, okay, right, I'm at the bottom. I'm going to feel heavy. Why are you going to feel heavy at the bottom?
Most acceleration is being acted on you.
Because not only do you have to overcome gravity, what else do you have to have?
Force of centripetal
Yeah.
force.
So you have to have two forces making you not either move in a straight line or not fall down. Okay? So right now, you all are experiencing FG. Okay, that's what you all are experiencing right now is FG. So the total force, remember, is what you experience. So right now, you all are experiencing 1G. Cool. Okay? Now, imagine that I take the room and I start doing this. Okay? If I start doing this, what's going to happen at the bottom of that arc?
Feel more G's.
Yeah, you're going to feel heavier because when you hit the bottom, not only is gravity pulling you down, your body has to have that direction change so that you travel in a circular path. Okay? Now, at the top, how do you calculate your total force?
Minus force gravity.
Now, if you're going to complete a loop, what does the force total have to be greater than or equal to?
0.
Yes, it's got the total force at the top to complete a loop has to be greater than or equal to 0. Okay? So, if you set it equal to 0, then Fg equals force centripetal. This is where you go mg equals mv squared over r. What's going to happen to your mass? Cancels out. You get v equals the square root of GER. Okay? And that's the radius of whatever that loop is. Now, here's an interesting idea. This is where this comes full circle.
Circle.
If you plugged in the radius of the Earth, okay? If you plugged in the radius of the Earth, this would be the ultimate loop, okay? That would give you your orbital velocity at the surface of the Earth. So if you want to be in orbit around the Earth, so out of curiosity, somebody do this. Somebody take the radius of the Earth, 6.3713 times 10 to the 6, multiply that by 9.8 meters per second squared, and then take the square root of that.
7.90 times 7.
7 point.
Times 10 to the third meters per second, which is about 8,000 meters per second, which matches the coverage of the Earth. So imagine that I could throw this rubber stopper at 7,900 meters per second. If I could do that, I would throw it, it would stay in orbit, it would come right back to me, okay? But that's a little fast. Not to mention in our atmosphere, it would instantaneously vaporize because of the friction and drag. But this gets you minimum velocity. I promise you, I'm going to ask you a question. Something's going to be going into a loop. I'm going to ask you, is it going fast enough? There's a couple of different ways you can answer this. You could calculate the minimum velocity, and if that velocity is bigger than that, it's going to complete the loop. You could calculate the centripetal force. If that centripetal force is bigger than the weight, you're going to complete the loop. You could also look at force total equaling force centripetal minus Fg. If you wanted to get fancy, you could write that as MAC minus G. As long as your centripetal acceleration is bigger than 9.8 meters per second squared, you will complete the loop. So there's a whole bunch of different ways you can answer that question. Pick one, okay? Pick one. I promise you I'm going to ask you this. I'm going to say, hey, you're at the top of the loop. You want to feel a fraction of what you feel right now. So let's say at the top of the loop, you want to feel 1/8 of what you feel right now. Okay, you want to feel 1/8. So that's going to be 1/8 Fg equals force centripetal minus Fg. And then you solve that, you move that over, you get 9/8. I subtracted. You get 9/8 Fg equals your force centripetal. So you get 9/8 mg equals mv squared over r. Masses cancel out. You get the square root of 9/8 GER. I promise you, I'm going to ask you a question like that. The only thing that I will do different is that I will change that fraction. Okay? You might feel 1/2, 1/3, 1/4, something like that. You did an entire set of problems on this. Okay? It was the Vex vertical acceleration. You drew a graph. Okay? It was towards the middle of the page. I promise you, there's going to be something like that. Those are the big ideas. So here's what I have for your reviewing pleasure. Give that a turn. So there's two distinct parts. So this is just the centripetal motion part. On this one, you have a roller coaster that's going down an incline, and you're going to hit a loop. Don't worry so much about, like, I put the beginnings on there where you calculate the velocity when you hit the bottom. That's old school kinematic stuff. On the test, I'm not going to expect you to derive that part. I just put that in there to keep you kind of thinking that way. At the end of the day, on the test, I will give you that velocity. You just have to know what to do with it. Okay, so don't flip out and go, oh my God, I don't know, remember how to do inclined planes. Woe is me. I am so lost. Okay? No. Okay? No. I will give you the velocity on the test. You just have to know what to do with it. Okay? So, on this, if you do nothing else, I highly recommend that you look at question number 5 where you have 2 quarters sitting on a spinning object. Okay? So if nothing else, I highly recommend that you do number 5. There's also one on there where you have Bubba in a barrel, okay, where you're going to take, we'll use Al, okay. So Al is going to be spinning around like this, okay, and then as I slow down, Al crashes and burns. So what happens on that, remember, if you're stuck on the side of that barrel, here's the barrel, and I will tell you, it is like the whirling barrel of fun, something like that. Okay, you will know it exactly, and it will be Bubba. Okay, Bubba is in the barrel. Okay, second page, kind of the middle of the page. And I'm going to ask you, hey, what are the forces acting on Bubba once you drop out the floor? So when Bubba's like this, okay, remember, you're Bubba, you're like, oh, okay. If you're Bubba, what do you experience? What do you feel? It's the only time Bubba talks about his feelings.
Oh, yeah.
Pushed. You feel pushed, okay?
Oh, yeah.
So you're like this. Imagine the room is spinning. Okay, you're being pushed. Are you actually being pushed?
No.
No. What do you feel? Yes, you feel the barrel wall preventing you from going into a projectile, right? Okay?
Yeah.
Otherwise, you get shot out of there like a moon pie out of a shotgun, okay?
What?
If you've hung out with rednecks, you completely get that analogy.
Moon pie?
You never had a moon pie?
What's a moon pie?
Oh, seriously?
It's a pie that they make on the moon.
Shut up. It's basically 2 graham cracker like this, and you have marshmallow in between, and the whole thing is covered with chocolate.
That they make on the
Yeah,
moon.
it's called a moon pie. You can have caramel or you can have chocolate. I recommend the chocolate.
Okay.
Oddly enough, you can go to Cracker Barrel and buy them. Okay. No, true story. I'm not making this up. If you want good moon pies, go to Cracker Barrel. They have the best moon pies. Okay. It's a unique cultural experience if you've never been to. If you've never been to a Cracker Barrel, it's a unique cultural experience. That's all I have to say. So, make sure
Don't encourage it.
that you know what happens with Bubba in the barrel. Okay, there will be a Bubba in the barrel problem, and it will feature Bubba. It might even involve the word poosh. Okay, I'll have to work on the spelling on that one.
P-O-O-S-H.
So, anyway, give that a spin again. Then you're also going to have, for the second part, is the whole gravitational field set of equations. If you do nothing else, I highly recommend that you work question number 16. Yeah, because I say if a satellite has an orbital period of 3 hours, what is the centripetal acceleration? Okay, so I highly recommend that you do this last question because it's going to be more than likely this is how the last question on the test is going to play out. Let me give you a hint. Find the orbital radius first using that Swiss Army knife equation.
Which one is this?
What are you going to do with the 3 hours?
Convert it into seconds. Duh.
Okay.
Nice.
So if nothing else, if push comes to shove, I highly recommend that you do 16 because that ties in a whole bunch of other stuff. Anyway,
How many
that's kind
questions
of
is
the
it? Was it this?
so stop you on the camera.
Yeah, how long is the